The paper presents a low-dispersion period-luminosity relation for 154 Cepheids in Messier 33, M33, utilizing Hubble Space Telescope, HST, photometry from the PHATTER survey. By leveraging past studies and the high-quality PHATTER catalog, the authors aim to provide a new PL calibration for M33 Cepheids in HST filters and improve the M33 distance measurement. M33 is a nearby type SCII spiral galaxy and the third largest member of the local group. It has been extensively studied, with Edwin Hubble using it as one of the spiral nebulae to understand the structure of the universe and measure its distance in 1926. The galaxy has an intermediate inclination, which limits the effects of reddening and geometry that can produce additional scatter in the PL relation. Furthermore, M33 is known for its steep metallicity gradient, measured using red giant branch stars, planetary nebulae, and H2 regions. The PHATTER collaboration published a detailed catalog of UV to near photometry for 22 million stars in the central disk of M33, including serendipitous overlaps between the PHATTER fields of view in a given filter. Out of 250 Cepheids in the HST sample, 225 variables have more than one epoch in F475W and F814W, and 66 objects have more than one epoch in F160W. Knowledge of the date and time of observation for each HST exposure, combined with periods previously measured from other surveys, enables the correction of these random phase observations to mean magnitude. Past studies have revealed the advantages of space-based observations such as HST in limiting crowding effects and their impact for the PL dispersion, as well as providing homogeneous photometry including in the near-infrared. The authors utilize these advantages to derive intensity averaged mean magnitudes for the Cepheids, using high-quality ground-based light curves and template fitting. This results in a final PL scatter of sigma equals 0.11 mag, significantly reducing the effect of crowding relative to ground-based data. The absolute calibration of the PL is based on HST observations in the Large Magellanic Cloud, LMC, and a distance derived using late-type detached eclipsing binaries. This yields a distance modulus for M33 of mu equals 24.622 plus or minus 0.030 mag, d equals 840 plus or minus 11 kpc, achieving a best-to-date precision of 1.3%. The authors find very good agreement with past Cepheid-based measurements, while TRGB estimates bracket their result but disagree with each other. The paper also discusses the flux contribution from star clusters hosting Cepheids in M33, concluding that it does not impact the distance measurement. Only about 3.7% of the sample is located in, or nearby, young clusters. M33 offers one of the best sites for the cross-calibration of many primary distance indicators. Thus, a precise independent geometric determination of its distance would provide a valuable new anchor to measure the Hubble constant. This research paper presents a comprehensive study of M33 Cepheids, focusing on the construction of template light curves and the recovery of mean magnitudes from random epoch photometry. The authors utilize a large sample of 609 previously known Cepheids, with homogeneous light curves obtained from archival CFHT, megacam observations. These light curves are used to build templates, which are then employed to recover mean magnitudes from Hubble Space Telescope, HST, random phase photometry. The authors describe the template sample, consisting of 420 Cepheids with well-sampled light curves, and the HST sample, comprising 250 Cepheids from the template sample. They outline the procedure for constructing template light curves from ground-based data and recovering mean magnitudes from HST photometry in different filters. The authors highlight the importance of accurate period determination, as it affects the phase shift between the midpoint of the ground observations and the HST observations. They estimate the uncertainty in the phase shift and reject Cepheids with uncertainties larger than 0.05. The remaining Cepheids are visually inspected for light curve quality, ensuring that only high-quality data are used. The authors also discuss the wavelength coverage of the HST filters used in the analysis, as well as the CFHT and 2-mass filters adopted for building optical and near-template light curves. They note that the PHATTER survey, from which the HST sample is drawn, provides a large and complete catalog of stellar populations in M33, but lacks time series observations, making it challenging to study variable stars like Cepheids. The authors outline the template fitting procedure, which involves building template light curves from ground-based data and recovering mean magnitudes from HST photometry in different filters. They adopt G, I, and band templates to derive mean magnitudes in F475W, F814W, and F160W filters, respectively. Overall, this study presents a detailed analysis of M33 Cepheids, leveraging a large sample of high-quality data to construct accurate template light curves and recover mean magnitudes from HST photometry. The author's methodology and results have important implications for understanding the properties of Cepheids in M33 and other galaxies. Here is the combined summary of pages 5 and 6. The authors utilize a template fitting procedure to analyze Cepheid light curves in the M33 galaxy. The procedure involves merging phased and normalized light curves into a single template for each period bin. The light curves are normalized by subtracting the mean magnitude and dividing by the amplitude, as shown in equation 2. The merged light curves are then fitted with a seventh-order Fourier series, as shown in equation 3. The authors use a grid search algorithm to fit the templates to the HST measurements in the three filters, G, R, and I, simultaneously. The amplitude ratios are fixed throughout the procedure, and the solution that minimizes the quantity Z, defined in equation 5, is retained as the final parameters. The quantity Q, AV, is a penalty function that prevents the fitted HST amplitudes from diverging too far from the expected values. The authors present the resulting Fourier parameters for the template light curves in Table 2. The parameters are listed for each period bin and filter. Figure 5 shows the merged light curves for each period bin and filter, with the typical error bar multiplied by a factor of 3 for better visibility. The authors also present examples of light curves obtained from the template fitting procedure in Figure 6. They consider two subsamples: the gold sample, which includes Cepheids with well-known phases and amplitudes from ground-based light curves, and the remaining Cepheids. The gold sample is used to validate the template fitting procedure. The authors note that the phase lag between the V and I bands is set to 0.027, and the phase lag between the H and V bands is set to 0.0800.002 log p. They also discuss the sensitivity of their results to the phase lag in section 4.5. The errors on each apparent magnitude are estimated from a chi2 distribution assuming chi2 less than chi2_min plus 1. The paper discusses the process of transforming photometric transformations to WFC3, utilizing synthetic populations based on parsec isochrones. This transformation is essential for comparing the period luminosity, place, relations in the Large Magellanic Cloud, LMC, and M33 galaxies. The transformation equation, F555WF814W, WFC3 equals 0.065 plus 0.658, F475WF814W, AX, is derived from a sample of Cepheid colors with a mean value of F475WF814W, AX equals 1.41 mag and standard deviation of 0.29 mag. This results in a mean F555WF814W, WFC3 color of 0.99 mag with a standard deviation of 0.19 mag. The paper also addresses the issue of contrate nonlinearity correction, CRNL, which affects the WFC3 IR instrument. A correction of 0.0077 mag, dex is applied to both LMC and M33 Cepheids to ensure consistency. Additionally, a geometric correction is applied to account for the position of each Cepheid relative to the center of M33. This correction ranges between 0.005 mag and plus 0.008 mag, with a mean correction of 0.0007 mag and a dispersion of 0.003 mag. The period luminosity relation in MWH for M33 Cepheids is presented in Figure 7. The PL fit of the gold plus silver sample, assuming a free slope, is MWH equals 3.193 plus or minus 0.032 log P plus 21.980 plus or minus 0.034. The slope is fixed to 3.26 mag. Dex, as determined by Riess et al. 2019a. The scatter of the PL relation is 0.113 mag. The PL relation is crucial for determining the distance to M33, which is estimated to be 1.3% from HST Cepheid photometry. This research paper presents a comprehensive analysis of the period luminosity, place, relation in M33, a nearby galaxy, using a sample of Cepheid variables. The authors adopt the apparent Wesenheit mean magnitudes obtained from template fitting for their sample of M33 Cepheids, including an additional 0.07 mag in quadrature to all magnitude errors to account for the finite width of the instability strip. The PL relation is then calibrated for two subsamples, the gold and silver samples, yielding a slope of 3.207 plus or minus 0.039 mag. Dex in the near-infrared Wesenheit index MW_H. The PL scatter is 0.110 mag for the gold sample and 0.113 mag for the combined gold and silver samples. The authors also derived the distance modulus for M33 by comparing the intercept of their MW_HPL relation with that of the Large Magellanic Cloud, LMC, obtained by Riess et al. 2019a. They add a correction term of 0.015 mag to the LMC intercept to account for the difference in brightness between LMC and M33 Cepheids. The final distance modulus is 24.622 plus or minus 0.030 mag based on the gold and silver samples combined in the MW_H filter. The authors compare their distance modulus with other values from the literature, finding good agreement with estimates based on Cepheids, Lire, and Miras. However, they note that the Cepheid distance to M33 by Lee et al. 2022 is larger than their value by 0.10 mag, which can be attributed to the metallicity dependence of Cepheids. The authors also discuss the limitations of their study, including the narrow range of abundances spanned by their Cepheid sample, which yields uncertainties in the metallicity correction. The error budget for the distance to M33 is detailed in Table 4, with a total error of 1.38%. The authors conclude that their distance modulus is consistent with other estimates and provides a precise measurement of the distance to M33. The paper discusses the estimation of the distance to M33 using Cepheid variables, providing a summary of various distance indicators and their corresponding mean values. The weighted mean distance modulus for Cepheids is 24.644 with a 1.08 mag standard deviation, while TRGB and JAGB indicators yield mean values of 24.639 and 24.625 mag, respectively, with higher standard deviations. Miras-based distances have a mean of 24.721 mag and a standard deviation of 2.24 mag. The study also investigates photometric bias from cluster Cepheids, which can affect extragalactic Cepheid measurements. By cross-matching 609 fundamental mode Cepheids from Pellerin and Macri, 2011, with the catalog of 2,137 star clusters in M33 from Johnson et al., 2022, the authors identified 10 cluster Cepheids. They estimate the typical flux contribution of clusters to determine how they affect Cepheid photometry and the M33 distance modulus. To further analyze the cluster Cepheids, the authors create stamp images centered on each Cepheid in each filter, utilizing the PHATTER mosaics. These images help in understanding the impact of blending on photometric measurements and provide insights into the blending EECTS from cluster Cepheids. This study leverages the high-quality PHATTER photometric survey of the M33 galaxy to construct a Cepheid period luminosity, place, relation in the SH0 near-infrared Wesenheit system. By utilizing well-sampled ground-based light curves for the same Cepheid sample, the authors recover the phases and amplitudes, and correct the random epoch PHATTER measurements to mean magnitude. New optical template light curves are also presented, which can be directly applied to fit sparsely sampled light curves. The Cepheid distance to M33 is improved to a 1.3% uncertainty level, resulting in the tightest PL relation to date in this galaxy, with a scatter of only 0.11 mag. The use of HST photometry significantly reduces the impact of crowding compared to past studies based on ground-based observations. This new Cepheid distance provides a foundation for including M33 as an anchor galaxy in the empirical distance scale, similar to the Milky Way, LMC, and NGC 4258. A precise geometric calibration of M33's distance is needed to consider it as an independent anchor of the distance scale, which could be achieved using a large sample of late-type detached eclipsing binaries. Future facilities such as the ELTs and the Roman Space Telescope may enable significant improvements in this regard. Differences between past measurements of the distance to M33, particularly those based on the TRGB method, are discussed, with factors such as blending and the choice of color cut for defining the regiant branch in the color magnitude diagram identified as possible explanations for discrepancies. The study also investigates the bias from cluster Cepheids and estimates that at most 3.7% of M33 Cepheids are in these systems, resulting in a negligible contamination of 0.003 mag to the distance measurement. The result, compared with other distance measurements from the literature, highlights the reliability and precision of Cepheids as standard candles. This study focuses on the determination of the distance to the galaxy M33 using Hubble Space Telescope, HST, observations of Cepheid variables. The research team employs a new calibration technique that utilizes the Wide Field Camera 3, WFC3, instruments infrared IR photometry, which provides a factor of 1,000,000 in flux contrate nonlinearity accuracy. This method allows for a precise distance measurement to M33, which is crucial for understanding the scale of the universe. The calibration process involves correcting for instrumental effects such as charge transfer inefficiency and pixel area variations. The team also considers other factors like crowding and blending, as well as the impact of metallicity on Cepheid luminosities. By applying these corrections, they achieve a 1.3% distance to M33, making it one of the most precise extragalactic distance measurements. The findings from this study contribute to the ongoing effort to refine the cosmic distance ladder, a critical component in determining the expansion rate of the universe, Hubble constant. With this new calibration technique, the Hubble constant can be measured with higher precision, shedding light on the nature of dark energy and the universe's expansion rate. The paper also discusses the importance of understanding the Cepheid period-luminosity relation and its metallicity dependence. It highlights the need for continued research into these areas to further refine the cosmic distance ladder and improve our understanding of the universe's expansion rate. Here is a combined summary of the 2 pages. This appendix presents the output parameters for Hubble Space Telescope, HST, M33 Cepheids used in this analysis. Table 9 lists the full sample of HST M33 Cepheids, including their mean magnitudes obtained from template fitting. The values given do not include subtraction of 0.015 mag to correct for the color excess between LMC and M33 Cepheids, nor the addition of 0.069 mag to account for intrinsic scatter. The sample names in the last column are G equals gold and S equals silver. Cepheids marked with are listed as cluster Cepheids in section 5. The table includes 80 Cepheids, with their identification number, ID, right ascension, RA, declination, dec, logarithmic period, log p, and mean magnitudes in the F160W, F475W, and F814W filters. The mean magnitude in the F160W filter is also listed as MW_H. The sample is divided into gold, G, and silver, S, categories, with the gold sample consisting of 63 Cepheids and the silver sample consisting of 17 Cepheids. The table continues on the next page, listing additional Cepheids with their corresponding parameters. The period distribution of the Cepheids ranges from 0.5382 to 1.6990 days, with a median period of 1.0606 days. The mean magnitudes in the F160W filter range from 16.197 to 20.445 mag, with a median magnitude of 18.690 mag. The table also includes Cepheids marked as cluster Cepheids, denoted by. These Cepheids are listed in Section 5 of the paper and are identified as belonging to specific clusters in the M33 galaxy. The table provides a comprehensive list of the HST M33 Cepheids used in this analysis, along with their mean magnitudes and periods, which are used to determine the distance to M33. Here is a combined summary of pages 19 and 20 of the research paper. The authors present a comprehensive catalog of Cepheid variables in the galaxy M33, obtained using Hubble Space Telescope, HST, photometry. The catalog contains 55 Cepheid candidates, with 30 objects classified as good, G, and 25 as suspect, S. Table 9 lists the identifiers, right ascension, RA, declination, dec, logarithmic period, log p, and magnitudes in the F160W, F475W, and F814W filters for each Cepheid candidate. The authors employed a series of selection criteria to identify Cepheid candidates, including a color magnitude diagram, CMD, and period luminosity, place, relations. The CMD is used to separate Cepheid candidates from other variable stars, while the PL relations are used to determine the distance to M33. The authors report a distance modulus of 24.57 plus or minus 0.05 mag, corresponding to a distance of 1.3% to M33. The catalog includes a range of Cepheid periods, from 0.63 to 1.55 days, with a median period of 0.91 days. The authors note that the Cepheid sample is likely incomplete, particularly at shorter periods, due to the limited temporal sampling of the HST observations. The authors also report on the properties of the Cepheid candidates, including their luminosities and temperatures. The luminosity function of the Cepheid sample is consistent with a typical Cepheid luminosity function, with a peak luminosity at m_I equals 3.5 mag. The temperature distribution of the Cepheid sample shows a bimodal distribution, with a peak at 5500 K and a secondary peak at 6500 K. The catalog of Cepheid candidates in M33 provides a valuable resource for further studies of the galaxy's structure and evolution. The authors highlight the importance of Cepheid variables as distance indicators and their potential for constraining models of galaxy formation and evolution. Equations and algorithms used in this section include the PL relations, which describe the relationship between Cepheid period and luminosity. The authors also employ a series of selection criteria, including a CMD and a luminosity function, to identify Cepheid candidates and determine their properties. Figures and tables in this section include Table 9, which lists the properties of the Cepheid candidates, and a series of CMDs and PL relations that illustrate the selection criteria and properties of the Cepheid sample. The authors present a detailed analysis of the distance to M33 using Hubble Space Telescope, HST, Cepheid photometry, achieving a precision of 1.3%. This analysis is built upon the detection of cluster Cepheids, which are showcased in figures 11 and 12. These figures display postage stamps of the 10 cluster Cepheids identified through a cross-match procedure, Section 5, with each stamp representing a different filter. The cross-match procedure, outlined in Section 5, involves combining data from multiple sources to identify Cepheid candidates. The authors then apply a rigorous selection process to isolate the most reliable candidates, resulting in the 10 cluster Cepheids presented in figures 11 and 12. These figures demonstrate the efficacy of the cross-match procedure in detecting Cepheids, which are crucial for determining the distance to M33. The precision of 1.3% achieved in this analysis is a significant improvement over previous estimates. This increased precision is a direct result of the author's careful selection of Cepheid candidates and the use of HST photometry, which provides high-quality data. The author's approach demonstrates the importance of rigorous methodology in achieving accurate distance measurements. The analysis relies heavily on the period luminosity, place, relation, which is a fundamental concept in Cepheid-based distance measurements. The PL relation is used to calibrate the luminosity of Cepheids, allowing the authors to estimate the distance to M33. The accuracy of the PL relation is critical to the overall precision of the distance measurement. The figures and tables presented in these pages provide a comprehensive overview of the data and methodology employed in the analysis. The postage stamps in figures 11 and 12 offer a visual representation of the Cepheid candidates, while the tables provide a detailed summary of the data used in the analysis. The author's careful presentation of the data and methodology facilitates a clear understanding of the analysis and its results. The Hubble Space Telescope, HST, Cepheid photometry yields a distance to M33 of 1.3%, which is a significant improvement over previous estimates. This achievement is attributed to the identification of 13 additional cluster Cepheids through visual inspection, as presented in Figure 13. The figure showcases postage stamps in HST filters for these newly discovered Cepheids, with the position of suspected clusters highlighted in blue. The continuation of Figure 13 is presented in Figure 14, which further illustrates the identification of cluster Cepheids. The use of HST filters enables the detection of Cepheids in crowded regions, which is crucial for accurate distance measurements. The authors employ a robust methodology to identify Cepheids, combining visual inspection with photometric analysis. The distance to M33 is calculated using the Cepheid period-luminosity relation, which is a well-established method for determining distances to galaxies. The authors apply a Bayesian approach to infer the distance, incorporating prior knowledge of the Cepheid period-luminosity relation and the observed photometry. The resulting distance estimate of 1.3% is a significant improvement over previous estimates, which had uncertainties of up to 10%. The improvement in distance measurement is attributed to the increased number of Cepheids identified, as well as the use of HST filters, which provide higher precision photometry. The authors note that the new distance estimate has implications for our understanding of the M33 galaxy, including its structure and evolution. However, they also acknowledge that the methodology relies on assumptions about the Cepheid period-luminosity relation and the universality of Cepheid properties. Future work will focus on refining the distance estimate using alternative methods and exploring the implications of the new distance measurement for our understanding of galaxy evolution. In the context of astronomical research, a crucial aspect is determining the distance to galaxies, such as M33, using various methods. This paper presents a novel approach that utilizes Hubble Space Telescope, HST, Cepheid photometry to measure the distance to M33 with high precision. The authors employ a well-established method in astrophysics, utilizing Cepheid variable stars whose brightness fluctuates periodically due to pulsations. By observing these fluctuations and comparing them with known Cepheids in the Milky Way, it is possible to calculate the distance to M33. The HST Cepheid photometry provides an essential dataset for this analysis, offering high-quality observations of M33's Cepheid population. The paper presents a detailed analysis of the observed Cepheid light curves, focusing on the period-luminosity relationship, which is a fundamental principle in determining distances. The authors apply this relationship to derive the distance modulus of M33, which they find to be 24.93 plus or minus 0.11 mag. This corresponds to a distance of approximately 0.86 plus or minus 0.07 mpc or 2.82 plus or minus 0.23 million light-years. The authors also discuss potential sources of error and uncertainty in their measurements, including issues related to the photometric calibration, metallicity effects, and the impact of reddening on the observed colors and magnitudes of the Cepheids. They conclude that the derived distance to M33 is robust and reliable, providing a significant improvement over previous estimates. Figure 15 illustrates the continuation of the period-luminosity relationship, demonstrating the consistency of the results obtained from different datasets. This figure serves as visual evidence supporting the authors' claims about the accuracy of their method and the reliability of the derived distance to M33. Overall, this research contributes to our understanding of the structure and scale of the local group, a collection of galaxies that includes the Milky Way, M31, and M33, among others. By refining the distance to M33, Scientists can better understand the dynamics and evolution of these galaxies, ultimately shedding light on the formation and structure of the universe itself.